Hi, everyone. This is Christian Millichap, and I'm an associate professor at Furman University in Greenville, South Carolina. And this is a talk for the Nearly Carbon Neutral Geometric Topology Conference. Specifically, this is part of the Teaching Undergraduate Topology section. And my talks collectively are titled Interdisciplinary Topology at a Liberal Arts College. So I am going to share my screen and bring up little slide presentation since I have some pictures, and I figure this will help keep me a little more organized. So again, interdisciplinary topology at a liberal arts college. The first thing I want to do is just recap quickly some of the things I talked about in my first talk. So first off, my background teaching topology. I've taught it 3 times if you're including a student tutorial. They've all been very small classes at liberal arts schools where maybe intro to proofwriting, one intro to proofwriting class is the background requirement. Hopefully teaching it next academic year. And I am planning to use the Adams Franzosa book, Introduction to Topology, Pure and Applied, that I talked about in my first talk. So that is my background teaching topology. And the other thing I wanted to mention was just, again, who are the students I have? Because this really motivates, like, what do I want some goals for my class to be, and how can I connect the student interests along with hitting on departmental goals of what do we want students to get out of this type of class. So again, I talked a little bit about the majors at the different math majors at Furman. We have 3 different math majors: mathematics, applied math, math econ. We have about 20 to 25 graduating seniors a year in our school of 2,500. And many of our math majors double major, a lot of them, especially the applied math students are frequently with also doing a hard science, but we've also had math majors that are doing math and Spanish, math and communication studies. So we do get a pretty big variety of interests. And the other thing to mention is we can't make our math major have too many requirements. Students frequently double major. There's general education requirements. There's actually a cap, I believe, on having 11 courses count towards your major at Furman, and we're at that cap. So we need to think about sort of flexibility in our major, and also what's based on student interests, which are varied, while thinking about what's really essential. The other thing I'll mention is, again, lots of interest in interdisciplinary topics, and data analytics, as I'm sure you're all seeing at your colleges and universities, is the hot item. And other than that, while we frequently do have students go on the PhD programs in math, that is not the main goal of our program. Our students are more frequently getting masters in math adjacent or applied fields and going into the workforce. So that's a little bit of background, but that helps shape what direction I want to take a topology course at Furman, which really sets up this motivating question. So as I mentioned this in the last talk. So how topology fits into the Furman curriculum has recently changed. As a couple of years ago, it was just purely an elective that had almost never been taught. When I taught it in 2020, it was the first time. So it was an elective that could count towards the regular math major, and that was it. I had a small class of 7 students. It was mainly math majors. I did have one student that was a math and physics major, really interested, who's in an astrophysics PhD program. I did have one econ major that was just interested in the topic, but otherwise it was math students that were really interested in learning about topology, which is great. But now it is a part of our core upper level math proofwriting curriculum. So regular math majors have to take either topology or real analysis. We sort of put those in a bucket together. So those are courses that will be offered every other year for our current curriculum. The applied math majors have to take, beyond an intro to proofs course, one upper level theoretical math course. So that could either be real analysis, topology, group theory, or a second level linear algebra course. Our first level linear algebra course has a little bit of proofwriting, but it's more computational. So with that in mind, this is really, how can we have a topology course that hits on these essential skills that our department wants? This is a theoretical math class. We want you doing proofwriting and digesting abstract definitions beyond an intro to proofs course and working on those skills, but also trying to connect things to the audience. I'll probably have more students just because I'll probably, rather than have 6 or 7, I'll probably have something more like 10 to 20 students in topology I teach the next time. But again, maybe 1, 2 are thinking about a PhD grad school program in math. A lot of them are going to be looking for math adjacent or more applied fields. So how can I make, without sacrificing too much of the proofwriting and abstract definitions and getting through some important content, how can I filter in connections that are going to really really connect to student interests at my school? And here are 2 simple things I've done and plan to do is, I think the Adams-Franzosa book is a great book for, the title is Pure and Applied Topology, to connect point set topology to some interesting applications and get students to reinforce and think about definitions and abstract concepts in different ways as we go through the semester. And the other thing is, rather than have a final exam, I've definitely moved to having a major project with a writing and presentation component. And if I have a little bit of time at the end, I'll talk about that. The one thing I'll say is that's much more time intensive than giving a final exam. I'm only willing to do that when I have reasonably small classes. I think if I got above, 20 students or so, I would not do the writing and presentation component where they're getting feedback and having meetings with me in the same way, just because it is very time consuming. But it's also been very rewarding talking to students about that. That's led to summer research projects they're interested, avenues for grad school of interest, connecting to adjacent topics for people in physics and economics where they really could dig into something. So, all right. So my goal is to talk about one of these applications to give you an idea of what you do in class. Oops. All right, there we go. But I figured just give a quick rundown of what I cover in my topology class. And this is referring to the Adams-Franzosa book. What do I cover in terms of point set topology? A lot of probably the essentials that people cover. There's a list with reference to the chapters. And then applications I try to cover are some below. And again, referencing to the chapters in Adams-Franzosa. And the one I want to talk about for the next 10 minutes or so is geographic information systems. I think this one's really cool. And it's something you can talk about pretty early on in the semester where things can feel very abstract for these students, right? The definition of a topological space, open, close, closure, interior, boundary. You'll have examples, but a lot of them are going to be, right, R2, R1, or looking at some of the weirder topologies. Maybe you'll go into topologies and the integers. So I want to talk about that geographic information systems application now. So let's hop into that. So what a GIS is before I go too far, I am completely borrowing from the Adams-Franzosa book. I'm following what they're doing there. I'm even borrowing pictures there. I am not claiming any originality there. But right, this is what we do. If we have good teaching ideas, we share it with one another and take what someone else did and mold and craft it to our class and our teaching style. So GIS, a computer system used to store, manipulate, and retrieve geographic data. So this could be, for GIS systems, a query or a question might be like, hey, if we have this simplified picture, which wetland regions are entirely inside a state park? And that's something that gets, some of these types of questions will get tricky for a computer, a little bit trickier, I think, for a computer to deal with or think how you describe. It certainly has to do with set intersections, but it's going well beyond just saying, hey, do 2 sets intersect non-trivially or not? Or is one set contained inside one another? So this one is, maybe that query is a little bit simpler, but these are the type of things a GIS might want to analyze. But again, some of these set relations are going to get more complicated than just, do you intersect or not? Or are you a subset of one another, right? You might have 2 areas and you're wondering, how do they overlap? Well, does one of them actually overlap in the interior with the other? Or do they just sort of have a common boundary that's maybe a road or a fence? That's getting a little more specific, but hopefully in the back of your mind, if you thought about topologies, questions about closure, interior, and boundary might be useful tools for encoding some of this, right? So I sort of think of this as this is a little bit of motivation, and there's a few pages from the book I usually have the students read the night before. But in my mind, the goal is like, hey, how can we analyze these spatial relations of sets overlapping, but one's ones that seem like they'd be relevant for talking about state parks, college campuses. But really using topological properties of closure, boundary, interior. And the whole time here, I'm thinking in terms of standard topology on R2. So your basis is the collection of all possible open balls using your standard Euclidean metric. So, all right. So leading up to this class, what have we done? We've done, definition of a topological space and examples, basis, open and closed sets, lots of examples of those, and then got into the definitions of interior, closure, boundary, and played around with some examples. But just a reminder, since we're going to be using this terminology and this notation, and if you haven't played around with this in a bit, here are the important definitions. And notice, right, interior, closure, boundary are very much topological definitions. They're defined in terms of unions, intersections, and complements of open and closed sets. So building up from your core topological definitions. So this is background. We have already introduced these definitions and played around with examples and proved some theorems about these heading into this application day. So in order to think about how could we carefully encode how things are overlapping or how boundaries are behaving, as I jump around there, or introduce this definition, and this is definition 2.16 in Adams Franzosa. If you give me two sets, I'm going to specifically say in R2, consider this 4 tuple. This is really gathering some information. So the first value is, let's look at how do the boundaries intersect, then how do the interiors intersect, then how does the boundary of one intersect with the interior of the other, and vice versa. And we're just going to assign a 4 tuple of where your values are 0, 1, just depending on whether this is empty or not. So here's a handful of examples, right? So the bottom left one, 1, 0, 0, 0. We know this was 2, and I'm going to think of just closed sets in the standard topology of R2 for now. Closed sets, partially because we're probably dealing with things where we have a defined boundary with either being roads or fences or natural features. Again, thinking about context here. So the 1, 0, 0, 0 guy, right, the boundaries overlap, but nothing else does. The 1, 1, 1, 1 guy, the boundaries overlap, the interiors overlap, and the boundaries overlap with each interior. The 0, 0, 0, 1 guy, well, let's take a look at that. This gets interesting because B is doesn't have any area, but you could take a look and think about, yes, these guys meet the criteria here. So we have some examples to play around with at first to share with the students. And here's this, these are all pictures from the book. You could the book has these 8, and you could start taking a look at them, discussions with students, making sure you understand, but doing some quick basic combinatorics tells you there's 16 possible intersection values, 8 of them are up there. Can we draw examples of closed sets A and B for the other 8? And this is one where I'm just like, either send, if you have mini whiteboards or you have board space, send students to boards and on their own in pairs, and let's just try to create guys that meet the other 8. I think this is a great activity. They're digesting definitions, abstract definitions, but in an explicit context. I think this is a great activity to do. So if you're interested, pause and think about that. But then it's also interesting to come back to the context of some of these closed sets that you create, and you can do all 16. Some of the closed sets you might have created are ones where you're like, well, does that make sense in the context of looking at states parks and college campuses and using GIS? So you might notice, right, a chunk of these examples have what I call whiskers. You can probably see those whiskers there. We're probably not thinking about having whiskers with the sets we're dealing with in GIS. So that leads us to start thinking about, like, well, how could we refine what sets we are playing with? How can we introduce a new mathematical definition that's meeting these features we want? So, right, in GIS, sets of interest usually have area. So let's try to restrict to closed sets that topologically meet this condition. And there's different ways you could go about this. The book has a definition. If you haven't wanted to spend extended time, or if you weren't using this book and is having this activity, it might be a great thing for students to try to think about how would you create the right definition using closure, interior, boundary, other topological ideas to hit on this idea. So here's a definition that starts going in the right direction. Set A for which, if we take the interior of A and then the closure of that, we'll call that regularly closed. Um, and hopefully you can think about this a little bit and see this removes those whisker issues. So on the left are examples of regularly closed, again, standard topology in R2. On the right are not. And this is helping us remove that whisker issue. But again, this could be a great activity for students to try to, you give them the motivating question, and as a homework problem or part of class, can we figure out what would be the right definition to do this? I think there's a lot of value in them thinking about how do we create definitions to meet the qualities we want. So this will naturally bring us back to the same question we had before of, hey, there's 16 possible intersection values. If I say you can just do closed sets, you can make all of them. But if I say now you've got to be regularly closed, so meeting more of the restrictions we probably want in an application, what can you do? And this is nice because it does really lead to a theorem you can prove. So these intersection values are not possible for regularly closed sets. So this is nice. We're doing an application. We naturally reach the question of, what sort of intersection values, and we have an actual theorem we can prove. So I really feel like, application and proof-based mathematics are coming together in this lesson. And this is just building off of your definitions and essential and basic ideas that you'd want students to be doing proofs in a intro points at topology class. And there's more to, proof involves unpacking definitions. There's more to build off of this. This is really hitting on what I will take one day to sort of cover what we said from, introducing this intersection value and some examples, having students play around to find some examples. And then I introduce the definition of regularly closed and maybe go through this theorem. You could certainly go to more, spend more time on this. And there's actually more in the section on the GIS section beyond this. So you could spend more time. Again, it's a game of me of like how much time to put in applications versus stick to core, point set topology curriculum, and also give students some time where they're exploring and thinking about ideas, and certainly not having a pure lecture-based class. I try to make sure it's partially inquiry, partially interactive lecture, but that's what works for me. People do different things. So other than that, again, this was a one-day segment I added in. Like I said, at the end of the semester, I do like to add in some projects. And again, I think this textbook has been a really good resource for that. So you can see at the end of, so this is the table of contents to intro topology, pure and apply. You can see at the end of each section, there's some examples of each chapter, of applications. But really chapters 8 through 14 hit on applications from connecting to a variety of areas of math, a little bit to cosmology and physics, a little bit to chemistry and biochemistry, digital imaging, economics. You see game theory and Nash equilibria. There's a lot for a starting resource for students to grab onto from here. And they do have references too. So this is, I'll just briefly bring this up. These were my project guidelines back from topology at Linfield. This is something where like I said, I had a class of like 6 or so. I had a lot of check-in points. This was a lot of work for me, but I also know it was rewarding for the students, and something we emphasize at our college is communication skills, both in terms of verbal communication and in writing. So this is something where they had an initial proposal and they met with me, that they had to submit and met with me to talk about. This is to make sure they had a topic that was reasonable, that they weren't biting off more than they could chew. And also they did something that was, this isn't so simple that, you could do it, you could figure this out in an hour and be completely done. I did have a writing report with a draft where they're using tech. And they did, instead of final exams, they had presentations those days. And I probably, and I did ask students to be active listeners, and there were some things they had to submit as part of that. These are the very brief guidelines, but I point them towards some project ideas, and most of it's coming from the textbook. Textbook is a starting point. So you can see some of them here. And I had students do a variety of things on this. I had a student do an introduction to braid groups and connections to topology. I had one student who was interested in going to graduate school for math and had an abstract algebra course dive into learning some very basic computational homology theory, but that's a great challenging topic for an undergraduate student. I also students definitely do a little bit of topological graph theory. I've had students in the past do different things with knot theory. And definitely the shape of space topic has always been a hot one too. But that's it. Well, thank you for listening, and hopefully I'll have some time to chat with you all during the conference weekend. All right.